Now let's discuss the tunneling process by using our WKB approximation scheme. So the problem is defined like this. Uh, so here I have a potential, and that potential is again slowly varying potential. So something like this. This is not having any bound state, so not necessary that it's a minimum. So something like this. Okay, and it can even come down. So I'm taking it for a particular case. To make the problem simpler, I am just taking a potential of this form, and I don't have any extension to this region. I just take the potential over this region. V is equal to 0, V is equal to 0. So actually you have to do the same problem when you are putting a potential like this when V is not equal to 0. So this is just for an illustration purpose. So right now our potential at this region is 0, so that I can directly go with the free particle equation. So when you have a slowly varying potential at this region, you have to go with the WKB wave function at this region as well as this region. So since I am taking the potential of this region as 0, so that means my potential is really not like this. This is something that you have to do. It's your work. What I'm doing now is something like this, and there is a potential inside. Here I have V equal to 0, V equal to 0. So this is region 1, this is 2, and this is 3. Okay. Now, what is the momentum of the particle at this region? P. It's not having any x dependence, it's a constant potential, and P is going to be root 2 me. So momentum is going to be that particular quantity, and my psi1 is quite easy here, not having any x dependence or anything. It's just like a e raised to I by h cross. You have your momentum, and momentum is constant, so I'm taking it p naught x plus b e raised to minus I by h cross p naught x. So this is actually the free particle equation, nothing different. We may be familiar with the form like ikx. So k is nothing but p naught by h cross. Okay, so same expression, nothing but written in terms of momentum. And p naught I know this quantity. So that is going to be the wave function at the region 1. Now, if you're thinking a classical case, when you have a potential something like this and or potential well like this, and you have a particle which is having energy, let's say something like this is energy, you have energy which is lower than this potential, so you never expect that particle to cross this boundary. However, in quantum mechanically, if we have a finite size for this potential, there is a certain probability that the particle can be seen at the region 3. So this process is known as tunneling, and we know alpha decay is a clear example of such kind of a tunneling. Okay, so psi1 is having two components, and this component is nothing but the component which is going in the forward direction. So this is the forward component, or you can call this as incident, psi incident. So the psi1, psi incident plus psi, this is the reflected component which is going backward. Okay, so that is my psi 1. What about psi 3? Third region, well, there is not going to be any reflected component here. Whatever fraction of this wave function which is being leaked out from here, it will be going in the forward direction. There is nothing to put it backside. So you'll be having some other constant. So A, B I kept here, C, D I'm keeping for psi 2 associating. So this is going to be e raised to minus, no, sorry, plus I by h cross p naught x. Momentum, there is no change. Here also it's free particle, here also it's free particle. Okay, so psi 1 and psi 3 are like this. Now what about this? How do we quantify this tunneling? Tunneling can be quantified in terms of a coefficient, nothing but our transmission coefficient, something that you know the definition from the electrodynamics course. So this is nothing but your amplitude square at this region divided by the amplitude square at this region, right? Your incident amplitude at this region divided by the transmitted amplitude square divided by the incident amplitude square. So that is nothing but here the amplitude of this quantity is nothing but e square divided by a square. This is something that we have to find out, transmission coefficient t transmission coefficient. Okay, so how do we determine that? That's the whole idea. So you know psi 1 and you know psi 3. Now you have to write the psi 2, and psi 2 we don't have any other option. We put this as a slowly varying potential, and our wave function has to be of the form of our WKB approximation. So I put that as a b c by root p of x exponential function it is, and it's going to be minus 1 by h cross from where x1, this is x1, this is x2. So x1 to x p of x prime dx prime plus another component can be there, which is d by root p of x, can be a positive exponential 1 by h cross x2 x2 p of x prime dx prime. Now let us say this area is a little bit wider, and if you want to normalize this wave function, uh, what happened with this component, the increasing exponential component? Well, let's say this is the area is extended further to x2 is up to infinity or so. If that is the case, this quantity is going to be a positive exponential, and that will not diverge. Sorry, it will diverge. That will not converge at any point. So that will make the wave function not a good wave function at all. So to be consistent, this term has to be 0, right? Otherwise, the definition of wave function is going to be not correct. Okay, so with that argument, I am neglecting this component, or this component is not there on my expression. So psi 2 is nothing but c by root p of x exponential minus 1 by h cross integral x1 to x p of x prime dx prime. Okay, so that is our wave function at the region 2. This is a WKB wave function. Okay, so once we have the wave function at 3 region, now how do we calculate their connection? We can just apply the boundary conditions here. So what is a boundary condition? At the boundary 1, uh, at x1, you can take, see, right now what we have taken is the potential is 0 here and potential is 0 here for making the problem simpler. But when you're doing, this is not going to be the case. I'll tell you how that it seems. So in this case, since it is a free wave function at my left hand side, I just have to take the boundary condition and apply the boundary condition. And here again at x2 I have to supply my wave function, the continuity condition of the wave function, and differentiability of the wave function. So both will give you two equations here, two equations here. So altogether you will be having four equations, and you will be having three unknowns. So that will be sufficient for you to solve the entire expression. So in the first boundary, that is wave function psi1 has to be continuous, has to be equal with the psi2 at that boundary at x equal to x1, and dou psi1 by dou x has to be equal to dou psi2 divided by dou x at x equal to x1. So you can take our wave function psi1, put the value x1 on that wave function, and that is going to be equal to your second wave function, which is here. Okay, so that will implies a e raised to I by h cross p naught x1 plus b e raised to minus I by h cross p naught x1 is equal to, you have a c at the second region and by root p of x. Okay, that root p of x, p of x is actually a variable, but at x equal to x naught it is having a particular momentum, right? That value I have to take something. I cannot put it in the variable form here, so I just have to take what is the value of the momentum corresponds to the point x1, because we are putting the boundary condition. So that will become something like root, I'm taking that value as a1. Now the exponential, and what else, minus 1 by h cross integral x1 to x p of x prime dx prime. Okay, something you have to put x1 over here. Once you put the x1 over there, that quantity is going to be e raised to 0, and that will not be there in that expression. That will not be there, so this is going to be the first equation that you are going to get. And same way, you take the differentiation of wave function 1 and 2 and make it equate it, and when you do that you will get an expression like this: I by h cross p naught into a e raised to I by h cross p naught x1, sorry, yeah, x1 minus b e raised to minus I by h cross p naught x1 is equal to minus c by root a1 into a1 you'll be having an h cross also. This term is coming from differentiating this exponential term over there. Okay, so this is going to be the second equation. So there are two equations which are connecting a b c. Okay, so by using this, combining these two equation, you can reduce one of the constants. So from this expression, I'll call this equation number 1 and this number 2. You can just multiply this equation with some I divided by h cross and sum these two expressions, so that this term will be cancelling b raised to minus I by h cross p naught x1. So that term will cancel away, and you can modify that expression and find out what is the value corresponds to any of the constant here. So uh, once you do that, you'll get c equal to, I'm not doing that calculation part now, so this will be something like 2a root a1 e raised to I p naught x 1 divided by h cross all divided by 1 minus a1 divided by I p naught. Okay. Similarly, at the second boundary, that is at x equal to x2, you apply the boundary condition. When you are applying the continuity of the wave function, you will get an expression like this. Then when you are having the differentiability at the boundary, you will get something like this. Okay, so we already obtained an expression that connects c and a. So here you have a constant c coming in this expression, where you can substitute whatever we got. Okay, and then the expression can be modified in such a way that you have to extract e by a from that expression. So this is a little bit of a step, mathematical step, to just find out e by a. And once you obtain e by a, that will be of this form. So there is a bunch of constants over here, and an exponential function which is I p naught x1 minus x2 divided by h cross, and yeah, another exponential function. This is exponential, and this is actually a sinusoidal component. Okay, I factorize the over. So e by a, the reason for finding out e by a is that the square of that will give you the transmission coefficient. So you take the square of that quantity, and uh, for this complex number, when you're taking the square, that will be disappearing from the expression. So that square will be acting on these terms, and that will brings you a constant like 4 by whatever this quantity, and an exponential where a 2 factor came because of the square, and whatever remaining minus 1 by h cross x1 to x2 p of x dx. So this quantity minus 1 by h cross, okay, 1 by h cross integral x1 to x2 p of x dx. I redefined it as a quantity gamma. So the reason why we are using is using gamma is because mostly whenever you have to deal with tunneling, your potential is going to be greater than whatever energy. That is, a instant when tunneling comes, the potential will be greater than the energy. So in that case, it's kind of convenient to introduce a constant which is kind of positive. So in terms of gamma, the transmission coefficient will become whatever this constant is, sir, and exponential minus 2 of that gamma. Okay, or the transmission coefficient roughly depends upon exponential uh, minus 2 gamma. So this is how the yeah uh, how do we find out the transmission coefficient for tunneling process. Now what we you have to do, or you have to attempt, is, see, this is actually a simple case. I skipped some mathematical part, but which are not complicated, which are uh, very basic things, and just rearrangement and sort of things like that. But you try to extend this potential into this region in the similar way, and again the same formation only, there is nothing different. The only thing is that instead of having the boundary condition here that we have taken, we have to use the connection formula to connect it with the region 1 and 3. So that means the wave function over this part, psi 1, is not going to be the free particle wave function. It's going to be the uh, our exponentially raising, yeah, exponentially decreasing component on, yeah, whatever it is coming. So that will be there at the region 1 and 3. Depending upon that, you have to choose it. So instead of boundary condition, you apply the connection formula, and you do the exactly same process. Apply the boundary condition to region for the wave function that you are obtaining for, and finally get into this value. Okay, transmission coefficient. So that is something that you can do by yourself, and if you have any difficulty at that point, we can have a discussion on our uh, live session. So by that, our WKB approximation is finished, and we have to get into the discussion of variation methods on the next class.